All right, good morning, everyone. Let us get started. We have quite a bit to go through. And as I had emailed you on Monday and advised you to have your notes available, I trust you have done so, and you will simply make the necessary notation in the notes so we can move through with some amount of efficiency. All right. Okay, so we start this morning on AC circuits. We start by looking at an RL circuit. So we have a resistor R in series with an inductor L, and it shows a current IS which flows through both. And of course, we know the principle of series, what we mean by components connected in series. Now, before I go any further, just to highlight that the principles, all the principles that we have learned so far, with voltage drop, series parallel circuits, etc., will be applied to AC circuits. The only difference is that we are now dealing with an alternating current, all right? We're now dealing with AC. And so that in of itself introduces some new principles in terms of we know it's shift from looking at scalar to vectors. So we're now going to be using vectors. And quite frankly, that's really the main difference. Okay, but all the principles. If we want the sum of if we want the supply voltage, then Kirchhoff's voltage law is going to apply. Just that no, when we add those voltages, we'll have to do so vectorially. All right, that's the only difference. All right, so moving along. So we have these two components, resistor and inductor, connected in series, and we have it across a supply Vs. And we know the two voltages VR and VL would be the voltage drops across R and L. And so if we consider the current, and from what we have learned so far, we know that the current is that reference quantity. So it will tell us, when we look at how the current is flowing, it is on that basis that we can make further analyses in terms of our circuit. So we have the circuit current IS, which is in phase with the voltage across the resistor. So the current IS, it's in phase with the voltage across the resistor. And to show that it is in phase, we simply draw the voltage across the resistor on top of the current, right? So that shows that they are in phase. At the same time, we have the current being out of phase by 90 degrees with the voltage across the inductor. And I reference here Lenz's law. Yep. And from your knowledge of Lenz's law, in a sense, it talks about having that back EMF, which is equal and opposite to the source producing it. Good. So I'm not using the law in its strictest sense, but it helps you to appreciate what we mean by lagging and leading. So for the current to be lagging, it means that it is behind the voltage. Or in other words, considering Lenz's law, we would see the voltage across the inductor before we see the current through the inductor. All right? So the voltage is ahead. You see voltage before you see current. That's basically what we are saying. And we determine this lag or lead based on the direction for positive rotation. So positive rotation is counterclockwise. All right. So when I now show the voltage, oh, sorry, going in the wrong direction, the voltage across the inductor, based on the fact that I'm using a phasor, what that means is that I've just frozen it in time. That's all it means. So we're frozen it in time. And by doing that, and remember, I is under VR, yeah? So that is still IS there. It's in phase, but we're not showing it. So it means that rotating this phasor, regardless of the speed of rotation, since they are operating with the same frequency, because we can only add phases if they're of the same frequency, all right? If regardless of the speed of rotation, it means that this angle, this 90-degree angle, will be maintained. So if the current is at that point, then it means that the voltage will be there. So we'd still have the 90 degrees. Okay, so it will always be 90 degrees out of phase. Okay, so from that, going back to the basic principle, going back to Kirchhoff's laws, we know that the supply voltage, yes, the supply voltage, Vs, is going to be the sum of the voltage drops that we have here. Still applying Kirchhoff's voltage law. However, in this instance, we are looking at the vector sum. And so that vector sum, all right, will be found by adding VL and VR. And to do that, we, of course, in this instance, we'll be using Pythagoras' theorem. All right. So over here, we'll also have VL. Yep. And we'll have our phase angle. Okay. So VL, or VS rather, is equal to V squared plus VL squared, which means that VS is equal to the square root of the sum of those squares. And if we look at the substitution for VR, again, just like we did before, the voltage drop across the resistor is going to be the current through it times the resistance. One thing I'm now introducing is that for the inductor, the voltage across the inductor, the voltage drop across the inductor is going to be equal to IS times XL. So I'm now introducing something new, which is XL, known as the inductive reactance. Yeah? And the inductive reactance there, okay, let's give me a minute, please. Okay, yeah. So the inductive reactance, we will speak about it in a few. But I'm now going to substitute for VR and VS in that equation. And so we have that ISZ. Again, I'm now introducing something new. So I've introduced it to XL, which is the inductive reactance. I'm now introducing it to Z, which is the impedance of the circuit. And that also is measured in ohms. Okay? So the impedance Z measured in ohms, yep, times the circuit current, okay, is equal to the square root. Remember, we are making the substitution for VR and VL. So in making that substitution, and of course, because, I need to say it the other way, because I was about to say because they are in series, but it's really the other way around. Given that the current leaving the resistor is entering the inductor, it means that they are in series. So it means that the current through the inductor and the resistor are one and the same, which is what we are showing here. So we can then substitute, the i's are canceled, and we're left with the impedance being equal to the square root of R squared plus Z squared, XL squared. And I see persons writing away, and all that is telling me is that you don't have the notes before you, because everything I have said so far is already in the notes. Okay? All right, so moving right along. I had drawn it earlier, but removed it, but I'm now returning it, which is phi, the angle phi, phase angle phi. And that phase angle is the inverse tan of the ratio of XL to R. And the other point we need to make about phi, right? I have it in orange, and I'm now circling it in red. So when we speak about phi, the phase angle, we are always, I repeat, we are always referring to the current relative to the supply voltage. So if I tell you that the phase angle is 30 degrees, what I am telling you, or 30 degrees leading, or plus 30 degrees, yes? What I am saying to you is that the current is 30 degrees ahead of the voltage. If I said it is minus 30, what I'm telling you is that the current is 30 degrees behind the voltage. So phi is always referring to the current relative to the voltage. Okay? Any questions on that? All right, so this is just a quick review. I know you have done complex numbers already, but we're just mentioning it here so that we can cover all our bases. What I've done is simply to superimpose what we just went through with the inductor and the resistor on the argon diagram. Yes? So the argon diagram, we have all 4 quadrants, but more importantly, we have the 4 axes. Yeah? So we have the positive real axis. So that's our 0 point. So your positive real, you have your positive imaginary, your negative real, and your negative imaginary. And based on the impedance diagram that we had, the impedance vector that we had XL on the positive imaginary and R on the positive real, as shown in the argon diagram. So here is XL, here is R. And the resultant is Z. So the argon diagram is what we use, as introduction to complex numbers. So what we're doing here is simply to introduce the use of complex numbers for circuit analysis with your AC circuits. So from the argon diagram, it means that Z is equal to R plus JXL. Again, because R is on the positive real axis and XL is on the positive imaginary axis. So we get the plus JXL. And now I go further to indicate that XL is equal to omega L, where of course omega is 2 pi F. So XL is equal to 2 pi FL. Or in other words, R is equal to Z is equal to R plus J 2 pi FL. I pause there. Any questions? All right, so let's move on. Okay, so take this question, please. All right, so we have a circuit here. We have 5 ohm resistor in series with a 32.8 millihenry inductor. And oh, that shouldn't be kilo ohms, that should be 5 ohms. I'm sorry. It should be 5 ohms. Okay. All right, so make that correction. Sorry about that. Okay, so we have a 5 ohm resistor in series with a 38.2 millihenry inductor, and that's across a 65 volt, 50 hertz supply. And we want the current flowing. All right, so we want to find our current I. Now, students, yes, it may not necessarily happen to you, but I think I have a responsibility to say it. One of the errors that most students make with this particular item is that they, instead of converting the inductance to inductive reactance, right? So they simply use a 32.8 instead of converting it to the ohmic value. Right? It's a common error. I've seen it year in, year out. So I'm just alerting you to it and hope that you don't fall into the same trap. So moving along. So we know that the circuit current is going to be given by V over Z. Yeah, where Z, we have introduced that as the impedance. Of course, in our previous topics, that would just simply be the total resistance, yes? In this instance, it's the impedance. So it's V over Z. And that impedance, based on the circuit we just looked at, it consists of a resistor and an inductor. And so it means that Z is equal to R squared plus XL squared. All right, nothing fancy. So we then need to determine the value of XL because we already have R. So XL is equal to 2 pi FL, which is approximately 12 ohms. And in calculating Z using Pythagoras theorem, Z would be equal to the square root of 5 squared plus 12 squared. Okay. So the magnitude of the current will be 65 over 13, which gives us 5 amperes. But of course, this is another key difference. Once you're dealing with AC circuits, we must indicate the phase angle. All right? So the current is 5 amperes, and the phase angle is 67.38. The question that you need to answer, however, is whether or not this phase angle should be a lagging phase angle or it should be a leading phase angle, meaning should it be positive or negative? All right, so all we have calculated here, given the values for XL and R, all we have calculated is the magnitude of the phase angle. All right, should it be positive or should it be negative? Okay. So how do we determine that? In this instance, we know that it's an inductive circuit. So from theory, what we just indicated, we know that the current will be lagging the voltage. So in a sense, this angle would be a negative angle, right? Just by virtue. so far, just by virtue of the fact that we know it's an inductive circuit. We know that it will be negative. But, you know, students, as we progress, what we're going to see is that when we have different combinations in the circuit, determining what the phase angle should be may not necessarily be as simple as I have now done it or shown. And so what we're going to do is to look at the use of complex numbers to do the same question we just went through. And here, using complex numbers, we know that Z is equal to R plus JXL. We know that XL is 12, so we have 5 plus J12. And if we divide the voltage by the impedance, we get this as our current. Yeah. Now, someone reminded me on Monday, and I think it's important that I highlight it. Unless it is otherwise specified. So you can make the note. Unless the angle for the supply voltage should be assumed to be 0. All right. So I may specify a voltage, whatever that voltage is, right? But unless you get that, you simply assume it to be 0, okay? And so we get I to be equal to 1.9231 minus J. Now, your final answer, once you're writing the answer for, you know, having gone through an AC question, your final answer must, and I trust you know what must mean, right? It must. If you do it any other way, you're going to get it wrong. You're going to get 0, irrespective of how accurate you believe your solution was. All right? It must be done in polar form. So the final answer must be in polar form. So converting I from rectangular to polar, we'll have 5 at angle minus 67.38. Now, in this instance, there's no need to wonder, do I have an inductive circuit, or, you know, do I have a lagging phase angle or a leading phase angle? Using complex numbers and using them appropriately, yes, you immediately will get the final answer in the form in which it should be given. Any questions? All right. So having spent the time going through the RL section, RL circuit, showing the link between what we did with Pythagoras and what we did with complex numbers, from here on, I'm going to drop the Pythagoras because that is something you would have known from high school, okay? You would have looked at complex numbers in recent times. Yeah? So we are going to use more of the complex numbers, yes, in doing our analysis. So for your RC circuit, where you have your capacitor in series with your resistor, all right? So we have our capacitor, we have our resistor. And I must admit that sometimes I use electrolytic capacitors, other times I just use your non-polarized capacitors. I'm not making an issue of that now because it does not impact the analysis that we're doing, okay? For that circuit, what we know is that the current is in phase with the voltage, and that will always be true. Voltage and the current, voltage across the resistor and the current are always in phase. Now, if you think about what happens when we charge a capacitor, if you connect a source across a capacitor, you're going to have a large current flowing, because that's when you're having transfer of charges from one plate of the capacitor to the next, right? And that results in a current flowing. Once the capacitor has now charged, then the current goes to zero, right? So the current gradually goes to zero while the voltage across the capacitor builds up. I want you to keep that in the back of your minds, because that helps you to appreciate the fact that you will see a current through your capacitor before you see the voltage. So for the capacitive circuit, or for the capacitor in the AC circuit, you're going to find that the current will now lead the voltage. So in other words, you see current before you see voltage. For the inductor, based on length, you see voltage before you see current. All right. And so it leads the voltage across the capacitor by 90 degrees, which is what we are showing here. Good. Similar to what we did before, you have the vector sum with VR and VC to give you your supply voltage. Yes. And we also have our phase angle, phi, which in this case would be inverse tan of XC over R. Okay. So using Pythagoras again, Vs squared equal VR squared plus Vc squared. Vs is equal to the square root of VR squared plus Vc squared. Making the substitution, and now I introduce something else, which is Xc, and Xc is known as the capacitive reactance. All right, making the substitutions, as before, we get Z to be equal to R squared plus Xc squared. All right, so for the inductor, we had Rc squared, R squared plus XL squared. That's for the capacitor, the RC circuit. We have Z being equal to the square root of R squared plus XC squared. Okay. And our phase angle, as I said before, quite similar to what we did earlier. Phase angle is given by the inverse tan of XC to R. And then jumping straight into the argon diagram. Note, XC would be along that path, and R would be here. So it means that R is on the positive rail. Yeah. That's what R. And XC would be on the negative imaginary. All right. So on the argon diagram, Z would be equal to R minus JXC. And XC is equal to 2 pi FC all to the minus 1. Again, I pause. Have I said anything that you're unclear on? Okay. So take this question for it, please. All right. So in this, for this question, I'm going to use complex numbers only. All right, we will not bother to go to the use of Pythagoras. So once again, V is equal to V over Z is equal to I, yeah, and R minus JXC is equal to Z. Okay. because this is on the negative j axis, so we get minus jxc. Okay. So we can calculate xc, 1 over 2 pi fc, which means that z is equal to 5, in this instance, 5 minus j12, which gives us a current of 1.9231 plus j 4.6154. And as I mentioned before, our answer must be in polar form. And so we get 5 at 67.38 degrees. So we know that it's capacitive. And for the capacitive portion, it's on the negative j. So that's the only consideration we need to make. And having done that, we have our impedance, and our answer tells us immediately that we have a leading phase angle of phi. In this instance, phi is 67.3.
Excuse me.
Yes,
Oh, this is the.
yeah, man,
the question you have 50, but in the yeah.
If you can type the question, do that, because we're not hearing anything you're saying. Can you type it?
Here,
I've muted you, Mr. Moore. We're not hearing anything you're saying. So if you could type the question, I can answer it. Have you typed it? Not seeing anything there. All right. What about the capacitance? 265.25. But I'm using 50 hertz. Anyway, it's correct. It's correct. We're using 50 hertz. All right, it is correct. Okay. All right. So we want to know, you have the axes in your notes, so I'm going to ask you to just to draw them. Yeah. Okay. So we have here reactance X. We're plotting that against frequency. Okay. Now you have the formulas. For XL, it's 2 pi FM. Good. Which means that there's a direct proportionality. Good. So for XL, it would be a straight line passing through the origin. Okay. And for XC, as it tends towards infinity, because there's an inverse relationship, as the frequency tends towards infinity, the capacitive reactance would tend towards 0, and the reverse is true. As the frequency tends towards 0, then XC tends towards infinity. And so to represent that, we show that it will be asymptotic. May not be the best drawn, but you have you understand the principle. Okay. we'll talk about this in a couple of weeks, but here, right? So that's a special frequency. Good. We're saying above that frequency, it means that you will have, if you have a series connection of these two, it means that this will be more inductive. And below that frequency, it's capacitive. Because of course, XC will be greater than XL. And over here, XL is greater than XC. Okay? And this is important for the next, especially for the next section that we're going to be looking at. Good? Because there, we're now going to look at a combination where we have all three, where we have R, L, and C connected in series. Right? So we have our resistor, we have our capacitor, we have our inductor. Each of them having a voltage drop. And as I said before, all the principles that we have learned so far, yes, applies. So within this closed loop, the EMF is Vs. And Vs would be equal to VR plus Vc plus VL. Just as before, sum of EMFs equals sum of voltage drops. All right? Nothing has changed. So with that said, we go to the next slide. And we use the same principles we applied to the two circuits we looked at just now. All right? So within the circuit, we first have our circuit current, which is IS. As we have already established, IS is in phase with the voltage across the resistor. And we show that by simply drawing VR atop of IS. All right? So we're still at this point. Excuse me. Let me use a different ink for this. All right, so we're still at that point. The current lags the voltage across the inductor. We just spoke to that earlier. So it means that the voltage across the inductor would be as shown. Remember, keep in mind, students, positive rotation. Right? And of course, since they're operating at the same frequency, it means that the angular speed is the same. Yeah. We can then freeze them in time and do our analysis. That's the basis on which we can use vectors or phasors, sorry. Okay. And then the current would lead the voltage across the capacitor by 90, as we had shown before. So we end up with this as our phasors for the series connections. Good. Now we're going to make an assumption. Right? We're going to make an assumption because what we are trying to satisfy, keep that in the back of your head, KVL. Right? That's what we're working on. So we're making an assumption, and the assumption here is that VL is greater than VC. It is not necessarily true, but we are just assuming it for the purpose of this morning's analysis. All right? So if we assume that to be the case, then it means that the resultant between VC and VL, which would be equal to VL minus VC, would lie along VL. Is that clear? If it's unclear, tell me, can I say it again? We're just finding resultant.
So you're saying, sir, that VL is greater than VC?
We're assuming that.
We're assuming. Okay.
All right. So we're making that assumption. It doesn't have to be. We're just making the assumption for the purpose of the analysis. So if that is true, then the resultant would be up here. I want to satisfy KVL, so I can now apply Pythagoras. And if I apply Pythagoras, I'm now finding the resultant of VL minus VC and VR. Good. So VS would be equal to square root of VR squared plus the difference between L and C all squared. But of course, since we are dealing with AC circuits, we can never forget phi. Right? There's no analysis that is going to be complete without phi. All right? But before getting to phi, let's make the substitutions that we have been making. All right? So in doing that, I get IZ squared is equal to IR squared plus IX minus IC all squared. All right. And so writing that in complex form, would be good. All right. We get Z to be equal to R plus J into XL minus XC. Now, students, although I started this analysis by saying that I am assuming VL to be greater than VC, although I made that assumption and it resulted in this formula, you are now being mandated It's not a word I use lightly, but when I use it, it is absolutely necessary for you to follow it. You are now being mandated to always, no wiggle room, to always write your impedance or the reactive portion of your impedance as L minus C. So you always maintain that. So you don't switch it around when you feel like. It must always be L minus C, XL minus XC. Is that clear? There's nothing to explain. It is something I'm telling you is mandatory. All right, so we can now deal with phi, now that we have gotten that out of the way. So phi is going to be the inverse tan of the opposite over the adjacent. The opposite obviously is VL minus VC, yes? Or if we remove the i's, if we substitute with the i's, right, we get tan phi to be equal to XL over R, or phi to be equal to the inverse tan of XL over R. Do you have any questions? Okay, so guess what? The first half in terms of the theory on AC circuits, we have just completed it. So now we move to see whether or not we understood what was being said. All right, so. Any volunteers? What's the first step?
Calculate the inductive reactance and inductive capacitance.
The inductive reactance and the capacitive reactance.
Capacity, yes. It's capacitive reactance.
All right. And that we have done. So we calculate XC and XL. And based on what we just did, yeah, we can now find the impedance. Because remember now, you know, this whole Pythagoras thing is a thing of the past. You can do that if you have a brain freeze during the exam, but we don't do that type of thing. So the corresponding impedance is R plus J into XL minus XC. And remember, we always have L minus C, XL minus XC. So it is 5 plus J12. So obviously we get back the same answer. Yeah? And so for this, we have now, one of the reasons I opted to maintain the values is that in finding XL and XC, or rather, for this circuit, we now have a combination of capacitance and inductance. The question is, which of them have the greater influence on the circuit? So we'll now need to determine if we did not use complex numbers. Yes, you would then have to say, okay, is it leading or lagging? Will the angle be negative or positive? Yes. But using complex numbers, we eliminate that need. So right away, we see that Z is equal to 5 plus J12. So calculating our current, we get 5 at angle minus 67.38. So it means that this is a lagging current.
So,
Yes.
so if the current is lagging, that means the circuit is more inductive.
Yes. All right. Any other questions? Anything else that I need to clear up before we move to the next stage? Yeah, we're doing well on time. That's good. Looks like we'll be able to cover all that we have scheduled for today. Okay, so no questions. Take this, and I want you, I'm going to give you 8 minutes to make an attempt. All right. Volunteer? Okay, then.
So may I go?
Well, that's one volunteer.
All right. So first off, we realize that we have the current value and we're supposed to find voltages in the circuit. So first we would find the inductive reactance and the
capacitive reactance.
Capacitive reactance. And those values are 12 each. And
so you got 12 for XL as well as XC?
yes, sir.
You sure about that?
Yes, 5,000.
Anybody else got different values for XL and XC? Or at least XC?
XC 15.
Yeah,
15
15 ohms to XC.
All right, so this is 12 and this is 15. But well, which means that your other values would be off
Would
a
be
bit, Mr.
incorrect. Yes, sir.
All right. Okay. So anybody who got the 12 and the 15? Carry on. Is it that you only calculated XL and XC and
no,
stopped?
so I should okay, all right. So once we have those values, we
Go
can
ahead.
then put it in the imaginary form. So V1
Complex
voltage
form.
complex form. So the voltage across V1 would be the current flowing through it times 5 plus 12J.
Okay.
Because we're putting it in that form. And the
Yes.
voltage across the capacitive part of the circuit would be the current times 8 minus 5J.
15.
15J, sorry.
Okay. All right, good. And that will give you V1 and V2.
Yes, sir. And from V1
So what
and
about
V2,
VS?
so because we have V1 and V2, we can use the voltage law, because V1 plus V2 would give us the total voltage in the circuit because it is closed. It's a closed circuit.
Absolutely. Good. Thank you.
Yes,
Very good. All right. What you said is correct. Everything you said is correct. But I would just, clean it up a bit, especially if I'm presenting it. So I would give, for example, this a name. I call it Z1. I call it Z2. So all of this would be Z2, and all of that would be Z1. All right? So Z1 would be equal to 5 plus J12, and Z2 would be equal to 8 minus J15. All right? Which you said. All right, so we have here the 12 and the 15. And then for V1, it is IZ1, and for V2, it is IZ2. And as he correctly said, V is equal to V1 plus V2. Right? And if you use complex numbers, all that he has gone through, all that he went through, is made a lot simpler. So you do your calculations using complex numbers, and then at the end is where you then put in or convert it to polar. All right? So let's go. So we have here XL and XC, 12 and 15. I put in the impedance because the impedance Z in this instance would simply be equal to Z. So Z would be equal to Z1 plus Z2, which is what we have here. That's a series circuit. And so when we're adding the complex, it is real plus real, imaginary plus imaginary. All right, so 5 plus J12, 8 minus J15. That gives us 13 minus J3. And if you multiply that by your 6, all right, 6 times 13 gives us 78. 6 times 3 gives us 18. So V is equal to 78 minus J18. All right, which we show on the other slide. And then I find V which is 80.05 minus 12.99. I'm going to confess, this is where I ended the class prematurely on Monday, right? And I hope I'm sure I won't have to do that today. Okay. Now, I'm going to show you what the phasor will look like. All right. So we calculated V. It is 80.05 minus 12.99 degrees. Okay. So drawing that phasor, because the question actually asks us to draw the phasor diagram. So if I draw that phasor, this is what it looks like. All right, because we calculated V and it is minus 12.99. That's not what I wanted it to see. All right. So let me draw the phasor. Let me sketch the phasor. So the phasor diagram for this would look like this. So this is I and V, and this would be 12.99. Question. And this question now we'll rescue the whole group. Okay. Do we have a leading or a lagging phase angle? And I want you to tell me why you're answering in that way. Is it leading or lagging, and why? Anybody? So then you're thinking deeply. But tell me, what is it? Does it have a leading or a lagging phase angle? So then let's start with you. And tell me why. The why has to be in it.
I would say lagging.
Why do you say that?
Because negative. Wait, me a second, sir.
Time up. 1 second pass already. Come again.
Give me a minute.
Don't have so much time. All right. Anybody else? Godling? Now that the mic is open, you need to use it, you know.
Sir, it would be leading, sir, based on
Cuddling. It's cuddling, we don't have all day, you know, we need an answer. All right, we won't waste any more time waiting on Ms. Cuddling. Who was giving me that response earlier?
Hopkins, sir.
Yes, Mr. Hopkins, go ahead.
Sir, I was saying it would be leading based on the
Why?
fact that the capacitive reactance is greater than the inductive reactance.
All right. Okay, fair enough, fair enough. That is, yeah, that's a reason. But I want something a little more fundamental. At least you have gotten it correct. But I want your reasoning to be a little different. And I want you to look at the phasor. I want it based on the phasor that I have drawn. You want to improve it? Dr. Hopkins? Based on the phasor.
I think what?
You want a minute too? So then minute done?
Oh,
You want an
if
hour now?
no, if it's by the phasor and not just the sign, I guess it would be because you would see the voltage across the resistor first.
No, we're not dealing with voltage across the resistor. We have several things, several components in the circuit. All right, so at least somebody got it correct. I just wanted an improvement on the reasoning. So if somebody can improve on the reasoning based on the phasor that is before you, then we can move on.
Sir,
Sir, is it the fact that the current would lead the voltage?
Okay. And how you know it's leading?
Because it said for a purely capacitive
Forget about the capacitance and
So can I-
inductance.
So can I say something?
Sure, Mr. Thomas.
Is it because we use the positive rotation and it is 12.99 degrees going the positive from the voltage?
And that is a significant improvement on the reasoning. At least here, I don't have a problem people getting things wrong, you know. What I have a problem with is people refusing to think. Right? So we have improved. So Mr. Hopkins gave me a correct answer. Right? I wanted it improved. Mr. Thomas has improved significantly on it. Now I want the expert answer based on what we have said since we started.
Sir, is it the quadrant that is in, sir?
No, not exactly.
Oh.
But in the interest of time, right? It is leading because we said on the third slide this morning that the phase angle is always given for the current relative to the voltage. So that is why Mr. Thomas's response was so much of an improvement. Because we are doing the positive rotation, yes? We are doing the rotation, the positive rotation, yes? Which means, yes, that the current, remember now, phase angle is what? Current relative to voltage. So the current relative to the voltage is 12.99 degrees ahead of the voltage. So it must be leading the voltage. Is that clear? All right. Moving right along then. So I can actually finish my lesson today. All right. So that is it. So that's your phasor. It's 12.99. Yep. So the current is leading the voltage. Again, positive rotation. Next. As was outlined earlier by Mr. Thomas, we have the voltage V1. It will be 6 times 5 plus J12. We get 30 plus J72. And for V2, we have 6 times 8. Now, if you look quickly, just add these two. So when you have it in complex form, you add them, immediately you get 78 minus J18, which is exactly what we calculated earlier. Yes? And then we put that in polar form, and we get these. So I can now draw all the phasors. So I have V1, I have V2, I have VS. Now let's draw them all. So we had that before. That was for the supply voltage and the current. And so the phase angle for the circuit is 12.99. For V1, we have a phase angle of 67.38. Of course, it's positive. Question, based on what we just outlined, with respect to the supply current and V1, is it lagging or leading?
Lagging, sir.
It is lagging, exactly, because we are looking at the current relative to the voltage. Getting the picture now? And then lastly, for V2, I mean, obviously, you know, I haven't done them to scale, but the angles to scale, right? So obviously, if for V2, we would have a leading current. So the current will be leading V2, it will be leading the supply voltage, and it will be lagging V1. So that's the, this is the okay. All right, since we know I've gotten over that hurdle, all right, I suppose you're drawing. Let me give you a minute to do that. So just for the purpose of the recording, let me just go back. For your power, the type is dependent on the component through which the current flows. And for active power P, measured in watts, that's the power absorbed by resistive elements. For your reactive element, the power absorbed there is known as the reactive power, and it is denoted by Q, and it is measured in vars. So this is all just information. Now, when we combine the active and the reactive power, when we combine the active and the reactive power, right? We refer to that as the apparent power. And that apparent power is denoted by S, and it is measured in volt amperes. So we have active power, P, in watts. We have reactive power, Q, in vars. We have apparent power, VA, or the apparent power, S, in volt amperes, all right, which is VA. In terms of the relationship between these three types of power, and I'm being very loose in my language. In terms of these various types of power, they are related as shown in what we refer to as the power triangle. And the only thing that you have seen so far this morning that is back in this diagram is that little fellow in the middle there called our phase angle, which is phi. So the relationship between apparent power S, reactive power Q, and active power P is shown in the power triangle. Now, again, this lines up quite nicely on our Argand diagram, because we see that Q would be on the J-axis. P would be on the real axis. Yeah? And S, of course, is what we are calculating. So S would be equal to a combination of P and Q. And that is shown. Yeah? That S is equal to P plus JQ. So S is equal to P plus JQ. And the phase angle phi, as I said before, is the same phase angle between the voltage and the current. So phi is what we would have determined prior. All right? Okay, we're running out of time. So the apparent pole is equal to voltage times current. And of course, the units would have told us that. Yep. So if the apparent pole is equal to V times I, if we look at the power triangle, the active power is given by S times cos phi. And then cos phi, we refer to that as the power factor. So the active power is equal to the apparent power times the power factor. That's basically what we're saying. And then finally, again, going back to the power triangle, the reactive power is given by S times sine phi, and there's no special name given to sine phi. So cos phi is your power factor. So P is equal to S times the power factor. So the question I just gave you, yeah, we're just going to work out the powers to see how all of this ties in. So if we continue the question that we just completed, the apparent power would be equal to V times I. And I was 6 minus J0, and V was 78 minus J18, I believe, yeah? So we have S equal VI, which is 468 minus J108. So based on what I just said, that S is equal to P plus JQ, then from this question, the active power P would be 468 watts. And the reactive power Q would be 108 VARs. But if you remember what we also said, we indicated that the type of power is dependent on the component through which the current is flowing. All right, that's what we said earlier. So we have calculated the power just using S equal VI. Oh, and I didn't use it, but just make a note of it. I'll come back to it in another class. I won't stress you with it today. But note I have VI conjugate. So it's VI conjugate. And I'll explain that another time. Don't worry about it just yet. All right. Even though I haven't used the conjugate in this question, if I had, it would have been 6 plus J0. Right, so it doesn't affect the solution that we have here today, but it's very important. So it's not just VI, it's VI conjugate. So the conjugate of the current that we use. All right, so if I'm now looking at the components, for the resistive part of the circuit, the total resistance in the circuit would have been 5 plus 8, which is 13. And so I squared R gives us 468 watts. Yep. And of course, for the reactive part, we have I squared X. X there would be the resultant reactance. Because remember now you had inductive and you had capacitive. Yep. And so I squared X would therefore give us 12 minus 15. And remember what we said earlier, you always maintain XL minus XE. And we therefore get the minus 108. All right, so we have a little time. So I'll just mention why we get minus 108. VI conjugate, what that is giving you is the power being supplied to the circuit. All right, so it's the power being supplied to the circuit. And that will be based on the source. So the source voltage was the 78 minus J18. We multiply that by VI, by I conjugate. We get the 468 minus 108. Now, if I am supplying minus 108, what does that really mean in our practical terms? What does that mean? If I'm supplying 108 bars, minus 108 bars. What does that really mean? If I'm giving out a negative, what does that really mean?
You're absorbing.
Absorbing.
Absolutely, absolutely. Which is what a capacitor really does. So a capacitor actually injects bars into a system. Now, well, they are first year students, so it won't make any difference to you at this stage. Right? But this is part of the operation in your factory setting, in your utilities. So if we want to reduce the amount of apparent power that we are using, we do a thing called power factor correction, right? So power factor correction involves you using, well, one method is you using your capacitors to reduce the VAR requirement for your facility. And so if you are reducing the VARs, let's go back to the power triangle. If I'm able to reduce the VARs, what is it that is going to happen to the angle? If the VAR is reduced, if this value is reduced, come on. If this is reduced, what's going to happen to phi?
Reduced as well.
Get smaller.
Right, so I get a smaller angle. Now, the line I just drew, I'm going to call that X. Is that line X shorter or longer than S, than the original S? Is it shorter or longer?
It's shorter.
Must be shorter. Good. All right. Next question. If I were to put in another line now, Y, would Y be shorter than X?
Yes, sir.
Good.
Yes, sir.
No. For S, X, and Y, has P changed? No. So P remained the same. No. Remember, what's the other name I gave for the active power? What was the other name I gave for the active power? Huh?
Real power.
What again?
Sir, active or real?
Real power. So I said it was a real power. So in other words, this is the power that you're going to need for your machinery. You can't escape that. That's the power you need to operate your factory. However, these lines, S, X, and Y, when they are reduced, what you are then doing is to reduce VI. And each time you reduce the length of S, what you're actually doing is saving money, because the utility company is billing you based on the VI product. Now that's for industrial facilities. So they bill you based on kVA, kilovolt amperes, or MVA, depending on your size. And what you're doing here, you're reducing the amount of reactive power that is being consumed. So if you can reduce the reactive power, and this angle phi is getting smaller. So if phi is getting smaller, what can I say about cos phi? If phi is getting smaller, what can I say about cos phi? If the angle is getting smaller, how does it impact the cosine of the angle? Hold on. Am I still talking to university engineering students who all needed to pass A-level maths in order to come here?
Cos phi the angle goes down, cos phi gets larger.
Thank you. So cos phi will tend towards 1, so it gets larger, which is why we say you're correcting the power factor. So the power factor is increasing if the angle is falling. And if the angle is falling, it means that you're using less apparent power to supply the same real power. Right? So that is how you would end up saving money in industry. Anyway, we're going to call it a day here. When next we meet, it will be almost like a tutorial, because I'm going to look at parallel and series parallel circuits. Yes, and then we look at some more complex networks and finding the power at different points, and we tie that together. So please ensure that you review what we have done here today. Instead of calling out this long list, I'm just going to